Cool. I'm Stewart. I'm currently at IBM working on OpenPOWER Firmware, and I'm going to talk about modernizing firmware testing. So you may be familiar with this Power CPU architecture, which hopefully you are, and Power 9 itself. And specifically, I'm going to focus on a system that's known internally as Witherspoon, but is publicly known as AC922 because you get product names and numbers rather than big long names there. And it's all about talking about firmware with pre-release everything. So when we look at problems during machine bring up and getting things ready to release, bugs can pretty much live anywhere. So the case itself at the bottom layer is probably usually okay. We haven't actually had to rework cases except for that one time on one system where you couldn't press the power button with the front of it on. It was hilarious. But usually the case is bug-free. The planar itself, so the motherboard there's definitely going to be revisions of that. So a bug in a system, that a problem could be because a component was missed off the motherboard. It's literally been a problem. You have to go in and solder a resistor onto there because it was missing in the original design. So the bug could be in the planar. The BMC, we've got a little BMC card off the side, so it's on board on the I was going to say Zaya/Barrel G2, but other systems it's a plug-in one. And we had new hardware on the BMC, so a new AST 2500, as well as OpenBMC, so a new BMC firmware stack. On P8 we had an AMI or Supermicro-based BMC stack, depending on the machine, and in P9 it's now OpenBMC on Witherspoon, and we still have AMI and Supermicro-based BMCs as well. But with an open source BMC stack, things are going to be different, right? It's not exactly the same as we've dealt with before. So bugs could exist between interacting with the BMC from host firmware, or could exist on the BMC themselves, or indeed you could run into interesting things related to the hardware there. RAM, the memory modules themselves, usually GA level, we don't actually have really pre-release memory, which is probably good. So you can usually trust the RAM to work. There can of course be bugs in the memory controller talking to the RAM, but we can definitely mostly count on them to work. The fans, believe it or not, we have revisions in fan assemblies and how we interact with them from the BMC. And of course, if you can't pump enough air out of it, you're not cooling things as much, so you're not going to get higher CPU frequencies. So a performance problem on the host that you think could be a firmware problem of, oh, you're not setting the CPU frequency, could actually be because the BMC isn't controlling the fans correctly. So we've had revisions in fans. One of the things, of course, we have is CPUs. So new CPU, new Power 9, we get first silicon, right? So we watch intently as the first wafer comes off the production line and it's cut up and put into modules, and we put it in a system, and then the job is to make it boot. And they're not just boot, but work something like a computer. We not only get up to a login prompt, but you have I/O going. And there's certainly bugs in first silicon. As anything comes off first, it's just like software, it compiles, doesn't mean it's going to work properly first time. With silicon, of course, you get a whole bunch of pre-validation checks and that kind of buzz, but problems can certainly be bugs in silicon, and that can be bugs that can be worked around. It can be bugs that, of course, require another silicon rev, or it can be, subtle firmware changes in some layers of the firmware to work around those kind of problems. And certainly, we find CPU bugs and they get fixed, or we work around them. And that means that, we've got another nice layer of uncertainty. We have PCIe cards. Believe it or not, with Power 9 stuff, not only do we have new PCIe Gen 4, we have new PCI cards as well. So there can be legitimate problems related to PCIe Gen 4 stuff on the chip that we could have bugs with, that we want to make sure we find and eliminate. There could be interactions with the cards themselves that are new, or the firmware that runs on the cards. So we've had issues that are actually fixed simply by updating the firmware on a pre-release PCIe Gen 4 card that then make everything work right from a host firmware perspective. And that's kind of an interesting thing there. And of course, not everyone considers upgrading their firmware on the PCIe card, as this includes when you're doing pre-release machines. We even have GPUs in this system, which of course we worked with NVIDIA, so they got first silicon on their GPUs. So at one point you literally had first silicon of the Power 9 on the first rev of a motherboard with first rev of BMC firmware with first rev of brand new GPUs, and it was pre-released everything first out the bat. And the miracle is that that ever booted, let alone actually worked and be functional. It's a real credit to engineering resources going on there, and of course then the process coming up to around about now is to find the big problems and eliminate them. So that was really sort of, where we started with, was pre-release absolute everything and go from there. And, my subset of firmware that I maintain interacts with a lot of these components. There are a lot of components of firmware, and I'll talk about that in a bit. But the real purpose of firmware is to never be noticed, right? The whole purpose is, if you're ever thinking about firmware, someone's messed up somewhere. It should be something that just works, because after all, you want the computer to boot. And this is the video recording of a P8 booting, because I didn't record a P9 in time, so I used the old one, but no one notices, right? Don't look at the magic behind the curtain. But the idea is you boot up and you can, boot an OS, and then you're done, right? And that's a bit faster than reality, but we're getting quicker on P9 as well. And of course, especially with things like the Coral Lab supercomputers and the like, they really do expect their computers to boot, as in anyone who's going to get one. They want it to boot, they want it to boot reliably. You want to always detect that the hardware is there, and that means you also want it to work all the time. The hardware there, and it's always going to work with that hardware and always show up and not have random problems as well. We also want it to perform well, so we have to do things like set up CPU frequency scaling and all of that kind of jazz as well. And the firmware stack for P9, of course, comes under OpenPOWER. So OpenPOWER started with Power 8, all under the OpenPOWER Foundation. And Power 9 had people involved in firmware bring up really early. So with P8, the OpenPOWER machine sort of came along sort of just as we were GAing sort of the IBM enterprise machines. Then there was the focus on the OpenPOWER machines. P9 stuff, like partners also had like first rev silicon. Like we were coming out the door working, hand in hand on firmware bring up. And so testing was not just for us, but to reproduce problems that partners saw and to find all the problems there. And so when does firmware start? So you might know what date it is now, or at least approximately what date it is. But this is when we first added support for the Witherspoon system, so the AC922, in the upstream host firmware. So this was, the first thing started shipping around December. We've got like big GA stuff coming up now. And about a year prior was where we actually had the code upstream. So we're talking about, talk about open. It's like not many systems you get the firmware a year before the box ships. And this is, possibly to the point where we had, one system somewhere with enough things in it to boot. I can't remember actually. Zaius was even earlier. So the partner machine isn't that one there. Its firmware was up like a month beforehand, right? So we're talking about, working with partners really early on and having a real, open power environment. The Google/Rackspace box was upstream a lot earlier, where a lot is a month. And this was sort of like the start of it. This would get you enough to sort of do the rest of firmware development, to basically say, let's find all the rest of the bugs and fix that. We also had OpenBMC. Say goodbye to proprietary BMCs. All fully open source firmware stack on the BMC is great. And I looked back and said, when did the OpenBMC work go upstream? So for Witherspoon, as in AC922, it turns out June 2016 is when the support for that went in. And that was pre even, like, I believe we didn't even have like motherboards for that yet. It was just the BMC card itself. So it's a removable card. If you go look at the AC922, there's a card with a BMC that comes out. So it's literally one of these on a desk with alligator clips into the power supply and a couple of other things off there, and you got the BMC running on that. And then it was, you of course could twiddle the right GPIOs to see whether the thing was booting and get all the initial bring up done, because once we got actual Power 9 silicon, of course, the BMC has to be able to turn the computer on or we can't do any development. And so that was when things started there. And I'm not really going to talk about OpenBMC, but the host firmware code is pretty interesting. So there's about 1.1 million lines of power-specific code on the host firmware. So on the firmware that runs on the P9 chip, there's about 1 million odd custom lines. And if you add up the entirety of the rest of the firmware components, as in build root that we use to build the environment, Linux, that we use a Linux kernel as part of our firmware to talk to all the I/O devices, because why write a separate device driver for firmware to be able to boot off a disk when we could just use the one in Linux and be done with it? So we do that. We use BusyBox in there, PettyBoot, which does the little UI to select what kernel to boot. If you add up all that, it's like 30-something million lines of code. And there's only about 1 million lines which are power specific. And this is sort of an advantage of sort of a very open ecosystem, as we just reuse open source code, contribute a whole bunch of it back, and be really smart about where we're spending our engineering resources. And of course, this 1 million lines of code is interacting with a lot of hardware, the P9 chip, which goes into a server, which is a lot of hardware. And then they have more hardware than not just the chip, but how do we go from there? So what do you do? How do you test it? How do you test this whole host firmware thing, combining with a bit of stuff there. Well, boots, ship it, right? Yeah, no, we can't really rely on on just that. It turns out you can have a lot of things still broken and still boot. If it reboots, then you should totally ship it. Like if you can not only boot the machine but reboot it, like that's perfect. And that's definitely not the standard that we hold ourselves to when shipping as an open source project, getting firmware out there. It is definitely a standard that is a joke and should only ever be a joke. But we also want it to make sure that partners who are producing machines, or other people who are producing machines, don't think that's sufficient. So tales from some other architectures is that people got to that stage where, oh, look at boots, that's it, we're fine to ship the computer. And then you're stuck as operating system engineers deciphering what random bugs and faults were in firmware and having to work around them. And we don't want that for Power. We don't want to have 1,000,001 firmware workarounds in Linux. We want to be able to have something that is a healthy open ecosystem that is well tested and has a good test suite behind it. And so going back, what was testing for Power 8? So Power 9 is different, as I mentioned, because partners are involved early on, and the OpenPOWER ecosystem is a lot larger than it was way back at the start. So what did we do for testing for Power 8? Well, Power 8 was much more started as sort of the monolithic development effort that you'd think of if it was IBM producing a Power CPU for enterprise systems, right? So it's sort of like a water flow of develop, test, ship, and you sort of loop around in the flow of development and test using large test teams of people. With anything that was automated, have it a lot more tied into very specific internal IBM environments, and not really something you could ship. So I found a number of problems with this, as how it would be for an open source project, and especially how it would be for something where we're delivering it to others. Right? We're having people involved in systems design and bring up really early on. We want to get them something that is, here, run this, that's a test suite. Not only here is your code, but also here is a test suite. So I mapped out the firmware development process to try and go, how does this all work and fit together? And here's a simplified view of OpenPOWER firmware development and how it all fits together. This is so simple that there's a little yellow box that just says Linux magically comes from this place. The blue bits are all Power-specific bits. Yellow is reuse from open source stuff, and down the bottom in the little pink circles is the firmware releases that someone would download off your manufacturer's website to install on your system. Right? So we have a whole bunch of different firmware development processes and components coming together that form one firmware image from a whole bunch of little components. And the bugs can literally be anywhere in the stack and flow down. Right? Just because you see something visible from an OS down the bottom, it could be way back in a component up here, or it could be a kernel bug over there, anywhere about. So what existing tests do we have? So we have HTX, which is a hardware exerciser, and its job is to basically find bugs in really low-level firmware, which we call like scan init, so setting up of the chip, as well as the hardware itself, as well as some problems with like putting machines under load. So it's a hardware exerciser that's specifically targeted for certain use cases. We have unit tests for firmware, so a bunch of our firmware stack does, of course, do unit tests on part of it. We have the Linux kernel that we ship in there, of course, has some self-tests in there, and we have KVM tests to test, that actually tests a lot of the hardware as well. And so we had a lot of sort of incidental firmware testing at this stage. You may see there, it's like, okay, we're testing the hardware, we're testing Linux itself, but are we explicitly testing a bunch of the firmware functionality and narrowing it down? And I found that we didn't really have something that brought this nicely together. We had things like, Travis CI, so this is like our Travis CI for Ski Boot, which is one of the firmware components. This builds and tests on a whole bunch of different distros, so we can say, yeah, we've got a wide variety of compatibility between GCC versions. We run a bunch of simulators in here and all kinds of nice jazz. We get code coverage testing. This is something I was been repeatedly returning to hack on and have just improved a whole bunch recently. So we can run our firmware test suite, which the big reveal will come later. But we can run our firmware boot and runtime testing as well as a unit test and get code coverage reportage out. So not only do you have an open source firmware stack and we'll have an open source test suite, but you can then go and look at the code coverage of running this against actual hardware and work out, are we actually testing all the things we want to test and we're thinking we're testing, and have good targets of where to add extra functionality. And interestingly enough, there's a bunch of really rare or never hit error conditions that are hard to test, right? Specific crash and memory corruption stuff. So we're never going to get to 100% code coverage, but it's very interesting to go back and dive into the details and go, are we actually testing the large chunks that we want to? And as a firmware maintainer, I want to answer the question of, will I regret merging this patch, right? We want to improve things, not ever regress functionality or performance. So my big question is, should we merge this code now, as in is it high enough quality that it won't break other people doing development work? Because when we're doing systems bring up, we have distro teams using it for distro development. We've got Red Hat using it for Red Hat development, right? We've got people doing it for performance work, trying to get a whole bunch of performance characteristics and optimization going on as well. So it's all pretty interesting, and we don't want to break other teams. We want people to run latest firmware possible, so we find out what's going on. The whole idea of catch bugs early and often, and we definitely want to do that in firmware. We want to make sure that we've caught the bugs as early as possible so we can fix them as close to possible, and preferably never merge anything with a bug. There's a lot of people who've been thinking like this, and as I mentioned before, we had partly automated testing out there inside IBM, but very much geared to an inside IBM environment. And we didn't have sort of really the ability to export, internal IBM machines and just go, everyone just log on to this specific machine in Austin with everything set up just right and run it against a machine. That's not going to scale for something like OpenPOWER. There were test frameworks, plural, right? People had gone and written a test and decided, I'll generalize it and convert it into a framework for writing other tests. The problem is 4 or 5 people had done that, and there hadn't been sort of a real overarching thing internally for that. So we had the whole X927 problem, as a friend gleefully puts it, which is the XKCD 927 comic, which is, there are 14 competing standards. I know, I'll create something that unifies them all. Now there are 15 competing standards. So we didn't want that. We didn't want to just have yet another testing framework and not bring anyone internally along. Because one thing about OpenPOWER is a bunch of IBM culture needs to change and be thinking of it as an open environment and a collaborative environment, not just something that produces an enterprise machine. So back in 2015, Andrew Geisler did the champion thing of grabbing a whole bunch of the internal code and getting it to a situation where you could run it, on a computer outside IBM without this specific setup environment, right? Without the custom file systems mounted all over the place and NFS shares exactly the right way. So this was the initial test. And so this was the thing that we're going to start off as a base of. And the whole goal was having testing for an open source project, as in OpenPOWER Firmware, should be an open source project, because we have not only us discovering bugs as firmware developers and OS developers, but we have partners doing it, right? You've got Rackspace doing bring up on their box and finding issues. We've got Google doing bring up on their issues. And what is the best way to report a bug? It is here is an automated test that reproduces it in a wonderful way. Now, the initial state of this test suite from the rescued internal code was possibly not ideal. I worked it out, and there was a Perl script that calls system-a-lot parsing XML with grep, which calls another Perl script via system parsing data via environment variables, which calls another Perl script to parse XML to work out what to pass to a shell script, which then constructs a Python script which then runs a test, for example, power on. And this was through a whole bunch of trying to grab things internally to get as much of test coverage as possible and have something that worked. So we wanted something that was a bit closer to this. If you're familiar with Python development, it's like you just run a unit test method simply, right? We want to say, if I'm working on one bug, I want to reproduce that one bug and run it easily and have code that looks really simple to reproduce it, right? You want to hand this to your hardware engineer whose job isn't writing Python code or writing firmware code. It is to find out what's going on in the hardware. And we want to say, here's a nice reproducible test case, and you can read it just because Python's pretty obvious. Or something like make check for C code, right? And so from going from this initial code dump, it was not just organizational change, but also a bunch of engineering work, right? We had test teams who still had to deliver products and do a whole bunch of test cycles that had their bits of automation around these things as well. So the running like HTX and KVM tests and kernel self-tests, all these kind of disjointed things. We had people working on this CI stuff. We had some people working on this all testing on actually really ancient distros, so a whole bunch of stuff only runs on RHEL 6. And of course, I wanted to do something that was runnable by anyone. So I have this theory about innovation tokens and spoon theory. Spoon theory is that you only have a certain number of spoons, and everything you do in a day costs a spoon, and at some point you've got no spoons left. And innovation tokens, I say, is when you're working on a giant engineering project, for example, shipping a Power 9 system, you have a certain number of innovation tokens you can spend. And if you overspend your innovation tokens, things go severely wrong when you try and out-innovate instead of just focusing on 1 or 2 solid areas. So I didn't want to do huge amounts of random innovation going on here. I wanted to do something that was really well-known technology, really easy to run, anyone could use. It wasn't, what you need is the latest version of this language compiler to then compile custom things and do that. No, we didn't want any of that. So we did a really Really, really simple stuff. It's just a bunch of Python 2.7, because that's like everywhere. Python 3 is wonderful, but not everywhere yet. IPMI tool, let's do as much over using the binary IPMI tool that everyone's going to use to interact with these machines, even though it would arguably be more efficient to have a pure Python IPMI implementation. No, let's use the actual binary. On the systems being tested, let's just use a bunch of standard distro tools. Let's poke using a normal FWTS, which is from Canonical, they use for firmware tests. We use the PCI utils and I2C utils and standard sensor utils, and have this vision of that tests are a deliverable. So that we deliver not only is, here a version 2.0 of OpenPOWER firmware that supports Power 9, we want to say at the same time, here is OP test version 1.0, and this is the test suite that goes along with it. So you have a release, which is the CPU, you have a release, which is the firmware format, and you have a release, which is the test suite. And then we could use that as a deliverable to also go into OpenPOWER Foundation and have here's a specification for firmware and a test suite to go with it, and codify that through code, right? That's the vision. And the strategy that we pursued for this is to slowly boil the frog. So none of the people who end up working on this realize that I've just co-opted them to delivering an open source firmware test suite. And that was the idea being to very incrementally add things to the test suite, start getting people to run it, make it be the obvious choice to do things, and then we totally just have this sudden OpenPOWER, open source, open firmware test suite. So short-term wins, add tests and run them. So we had myself and others starting to add little tests for things that we found along the way, and we started to run them and see when things would break or regress. And sort of indeed, when someone reported a bug, we just try and write small tests. So a bunch of early engineering work was just to set up some basic framework around it. So what do we test? On, off. Do we still boot an OS? If I run various commands, do we get the various output, like ls PCI? Do you get the same output each boot? As in, did we detect the same PCI devices each boot? That kind of stuff checks basic functionality. Change CPU frequency intentionally, check and actually measure that we're running the right frequency. All of that basic functionality, and then add on extended functionality. But do each things in a nice little module. So starting off from that sort of rickety spaghetti code going off, one major refactor later, we had something that completely looks like Python unit tests, except they're not unit tests, they test the machine. So it's sort of abusing the Python unit test framework, but it does end up looking like really familiar Python code. A whole bunch of other stuff let us take certain test hour time runs from 12 hours to 20 minutes, which was a nice thing. When I did that refactor and showed our one of our test teams, they're like, well, that's really useful. We can run a lot more tests now, and then we can break a lot more things. I'm like, yep, that's the goal. And they've proceeded to file a lot of bugs afterwards. And also, when we're in limited hardware, like we're doing early bring up in P9, you don't get a lot of them out the gate, right? This isn't yet mass production. Manufacturing's still sorting out how to make the thing, so you get a limited amount of chips, and you will be grateful for that. Thank you very much. So on limited hardware, running things as quick as possible is perfect. So we do some wonderful state machines internally to track the state of the computer and try and quickly detect when it's crashed and reboot it and continue running tests and all that kind of jazz. The desired workflow, which is literally what it is clone the repository from GitHub, enter the directory, run it, and point it to the firmware you want tested. So this is what I run dozens of times per day now, which is please log on to that host, flash that firmware on it, that BMC firmware, and run my test suite. So I have a script that will very quickly turn your computer into completely my computer. And so I'm one typo away of making someone else's day really miserable that will run none of their code anymore. My BMC code, my host firmware code, my OS with all my stuff there. It's remarkably efficient. I'm a little bit scared. But we've got it to that stage where basically every OPAL firmware developer now uses this just to flash the code, even if they're doing something else, because it's just simpler and it works quicker. It knows all of the intricacies of the different machines and the workarounds for various firmware versions to flash it. It's fantastic. And we had a lot of machines to test against. We wanted to run against Power 8 machines as well. We wanted to run against all the P9 ones, and we wanted to run on simulators, so that when we come and do the next chip, we can start running all of these tests as early in simulation as possible. And indeed debug things in simulators, because sometimes debugging things in a simulator is a lot easier than doing it in hardware. So that would be really neat. So what do tests look like? Let's show some code. So as I said, it looks remarkably like a Python unit test. And this test is a very simple one. It says, make sure the machine is off, as in go to state off, and then it says boot to the petty-boot shell. So petty-boot, you can exit to a shell. It's a good way to stop automatic boot. And if this fails, it'll fail the test. So this will simply do you boot? And if you boot, of course, you ship the machine, because that's obviously all you need to do. But that's the start of the test. The next test here is pretty interesting, because this one, believe it or not, is if you can boot 1,024 times. So it will just turn the machine off, turn it on, see that you boot, check if you get any errors in the kernel or firmware logs, and then boot the whole thing again. And when it gets to 1,024 times, it says your test is complete. Typically, we don't run to 1,024 because if boot takes 5 to 10 minutes, you can work out how long that takes. But even just getting to 10 or 100 is a pretty good thing if that consistently works, especially during bring up. So that's pretty interesting. We also have a new function called fast reboot, which takes reboot time from about 5 to 10 minutes to around 24 seconds. And that you can do. So we've had a Power 9 system reboot 1,024 times in a row in actually not much time. So it will reboot faster than x86 desktop systems, like using fast reboot. So we're trying to make sure that's also really stable and we can ship it as well. So that's exciting stuff. But this is the kind of test that looks like, as you can see, is normal code. And anyone who's like a user of a Power system could probably write this if they found a problem and wanted to work out what is this and hand it to us to help debug stuff. This checks that we didn't do something silly like enable an SSH server in PettyBoot. Turns out we missed that once in early development, and it's like, whoops, PettyBoot shouldn't be running an SSH server. You shouldn't be able to SSH into your bootloader. So this checks it by just running ps grep for dropbear on the PettyBoot shell, which is kind of nice. This test is one to do CPU frequency scaling testing. So basically what we do is we boot the machine, check what CPU frequencies are enabled, then for each of them, go and set them explicitly by disabling all the others and setting user space power governor. And then we want to check that we actually verify it. So we run ppc64 CPU -- frequency. We want to test that what we've actually running at, because it measures based on counting clock cycles, is roughly equivalent to the CPU frequency we set it to, within a margin of error. So this does that. And we actually catch bugs with this, where it's like, if you set a CPU frequency, it should be within that between this amount of time. So when we measure it, it should definitely be running at that frequency. And if not, there is a bug somewhere. And this is actually, even currently, actually, there's a bug that this test found, which is great. We also have the idea of creating torture tests, which is, don't just be nice to firmware by doing one thing at a time. Do a lot of things at once and just see when it explodes. And in the middle of all this work to start getting this going, we actually had a bug report on one of the enterprise systems that initially looked like a host firmware bug. It turned out not to be. It turned out to be a bug in the IPMI implementation on IBM's proprietary FSP stuff. But the way we actually found this and handed it to the appropriate team was one of our test developers wrote this is a cut-off version of it, but it's a multi-threaded test that starts a whole bunch of harmless IPMI commands from about 10 different threads, running them in a loop against the one machine at the same time as spewing a whole bunch of data out the console on the host, right? And then after that, about 10 minutes later or 20 minutes later, everything goes very, very poorly and you can't talk to the service processor anymore. And so we handed that to that engineering team, and that was what they needed, because they could actually then put on a debug version of the code on the FSP, find where it was crashing and fix the bug. So we can actually do more sophisticated tests now. We're looking at bringing this. They're actually using this now as to also test the OpenBMC IPMI implementation as that's being brought up. So that's pretty cool. We're seeing a lot of value here on that one. And we're going to use it for OpenPOWER stuff as well. So we want to have the power of being able to do like full Python stuff to be able to do like powerful tests where it's not just run command, check result, but run 100 commands at once and check that things don't explode, and have a way to bisect that down to simpler things and have variables in there. So it's kind of cool. SOL session closed by BMC. If you're familiar with some BMC implementations, you will cry every time you see this. But basically, we get to work around a whole bunch of BMC bugs, especially during bring up and early BMC code. So we have a bunch of code in our test suite to work around. And this is, if you ever have to understand what this code does, something has gone terribly wrong in your life, and I'll be there drinking with you. But we work around a bunch of BMC bugs. So that we can continue with our host firmware testing. And we do this in a bunch of places. And then we can also give it to the BMC development folk and go, here's your bug, you might want to fix it. And the good news is that with OpenBMC, that's a much more realistic prospect. We can go and fix things. There's a great bug that we have, which is a 20 megabit serial port versus the Linux TTY layer. It turns out that the Linux TTY layer was never built to deal with a 20 megabit serial port. And we use a VUART, so a virtual serial port on P9 systems. And that can run at about 20 megabit. And it turns out that we definitely hit some old kernel bugs that have been there since, I don't know, sometime in the early 90s. But that's been kind of fun as well. So we can literally do that. I've handed that to the BMC developers. Test coverage is looking pretty good. Current state of adoption is also pretty good because like developers are using it, test teams are using it, OpenBMC is using it. Talking to a whole bunch of OpenPOWER partners who are like really excited, and this will form the basis of sort of firmware certification stuff for a whole bunch of OpenPOWER stuff. So we're looking at doing that through the foundation, through not only OpenPOWER Ready, which is already mentioned in, as we're getting that in advance, but sort of an actual certification suite as well will be sort of the output of this test tool, which will be what developers run, which is the fantastic thing of like basically if I want something to work on production machines as a developer, I put it in this and it's instantly part of certification suite. So, pretty easy to run. There's documentation even, but you can see that that's not a complex command to run. It's just some stuff there. It's up on GitHub. So you can write your own tests. You can run it in a simulator even. If you don't have real Power 9 hardware yet, you can still write firmware tests, which is fascinating. I should really blog the intricacies of getting that set up with the right QEMU branch. And thank you. If there's any quick questions there, I think we're right at the end.